system, right? Module number 3 was free undamped single degree of freedom vibratory system. Okay, so as far as the last lecture is concerned, so we have I have explained you the introduction to the damping. What is damping? What are the elements? Okay, so you can see in the picture what are the elements of the damping. So that also we have seen in the last lecture. Okay, so basically three basic elements: K, C, and M. Mass is governed by mx double dot, spring is governed by kx, and damping is governed by damping force cx dot. So equation of motion becomes mx double dot plus kx plus cx dot is equal to 0. This is what we have understood yesterday mathematically, right? Okay, so I have just revised what we have studied yesterday, right? Uh, then I have explained this graph. This graph, what is transient state, what is steady state, right? What is output and all. Okay. Then two important parameters, omega d and logarithmic decrement del. Okay. So basically, we will be deriving the formula for the omega d and we will be deriving the formula for the del. Okay. So yesterday we have understand what is omega d and what is del, right? Okay. Then I have told you that we will be studying two types of damping. One is the viscous damping and second is the friction damping, or you can call it as a Coulomb's damping, right? So what is viscous damping? We have understood yesterday, and this is the example I have shown, that is a automotive suspension system, damper, or you can also call it as a shock absorber, right? So this we have studied. Then I have explained what is F. What is you can see the mathematics behind the damper. So F is directly proportional to x dot. So F is equal to cx dot. Okay. So we started with the first derivation, damp free vibrations with the viscous damping, right? So we have considered this diagram. I have considered this diagram. Then I have drawn a free body diagram for this mass. Okay. I have applied D'Alembert's principle. So mx double dot plus cx dot plus kx is equal to 0 is equal to 1. I have got. So this is a linear second order differential equations, right? See, I need to continue this derivation. That is why I am giving you the revision of the last lecture, because the you can say this derivation is not over. Okay, so that is why I am repeating this. Okay, so what is the solution? Initial solution: x is equal to e raised to st, x dot x double dot I got, fine. Then when e is equal to natural logarithm, s is equal to constant, t is equal to time. Okay, so finally I got this equation, equation number 2. I got this equation. What is that equation? ms square plus cx plus k is equal to 0, and this equation is also called as a characteristic equation. This is a second order equation, highest power is 2, so it will have a 2 roots, and this is also called as a frequency equation. Why? Because these 2 roots will give you the 2 frequencies basically. Okay, so then finally I have used this formula minus b plus minus regular mathematical formula to calculate the 2 roots, and I have got these 2 roots, h1 and h2, right? So what are the 2 roots? Plus and minus. I have got 2 roots, h1 and h2, right? Now basically since there are 2 roots, I will be having the 2 solutions, e raised to h1 of t and e raised to h2 of t, right? So what is the general solution? X is equal to a into e raised to h1 of t plus b into e raised to h1 of t, where a and b are nothing but arbitrary constants. So our next step is to find out, already we have find out s1 and s2, our next step is to find out a and b, that is the arbitrary constants. Okay, so that we have seen. Then finally, to solve this, to do the further analysis, we have to define two certain you can say terms. The first is critical damping coefficient. So already I have defined yesterday what is critical damping coefficient. It is denoted by Cc. So you know that at C is equal to Cc, the frequency of damp free vibration means what? Omega d is 0 and the motion is periodic. So this term is equal to 0. Square root of C upon 2m square minus km is equal to 0. So when this term is equal to 0, you can say that C is equal to Cc, and the corresponding term is called as the critical damping coefficient. Okay. So that also we have seen yesterday. So after analyzing, I have got two formula. One is Cc is equal to 2m omega n and Cc is equal to 2 into square root of km. So both this formula will be using for solving a problem on module number 4. That is free damped vibratory system. Okay. So then guys, yesterday I have defined damping factor. Now what is damping factor? Zeta. So it is mathematically ratio of C upon Cc. So from this what I have got? From this I have got C by 2m is equal to zeta into omega n. Okay. C upon 2m is equal to zeta into omega n. This is very, very important term because this I have to replace somewhere. Okay, so where? So finally, Finally, what are my roots? H1 comma H2 is equal to minus C. Here, instead of zeta into omega n, you have minus C upon 2 into omega n. Okay, so putting C upon 2 omega n, zeta into omega n, guys, you are getting two roots. H1 is equal to minus zeta plus square root of zeta square minus 1, omega n is common, minus zeta minus square root of zeta square minus 1, omega n is common. Okay, now basically I have two roots. Now basically I have told you that the nature of the system depends upon the value of damping zeta. What is the nature of system? There are two types of nature. One is oscillatory and second one is exponential. So oscillatory and exponential, whether the system is behaving oscillatory or whether the system is behaving exponential, where in the transient state. Transient state means what? Initial phase. Every system passes successfully to the transient state phase and it reaches the steady state. We call it as a stable system. And as an engineer, we should always design a stable system. Okay. Now basically, depending upon the value of damping means zeta, depending upon the magnitude of damping, there are three types which occurs: overdamped, critically damped, and underdamped system. So guys, in today's lecture, we will understand these three types one by one. Okay, so I hope you have understand the revision which we have taken the last lecture. You can also watch the corresponding live video also. Okay, chalo. So first case is overdamped system. So what do you mean by the overdamped system? Overdamped system means what? Basically, there are three things which you have to understand in case of the overdamped system. First is zeta should be greater than 1. Okay, zeta means what? Damping factor, that is C by Cc should be greater than 1 because zeta is C upon Cc. Second thing is what? Now already guys I have explained in the last lecture that the nature of the system, that is whether it is exponential or whether it is oscillatory, whether it is exponential or oscillatory, depends upon the nature of roots. So first of all, we will understand what are the nature of roots. So roots are real, unequal, and negative. See, after derivation, we'll be deriving the roots for the old time system. I'll be getting these roots real, unequal, and negative. But initially, I'm just telling you what type of nature we will be getting. So what will be the nature? Real, unequal, and negative. Now basically, when the nature of roots are real, unequal, you know, na, the roots can be real, roots can be complex conjugate. I think you know the difference between the both. Okay, roots can be positive, roots can be negative, roots can be equal, roots can be unequal. So depending upon that, what is the output? Output means what? Output is in the transient phase. It is purely exponential. So overtime system is nothing but zeta should be greater than 1. Roots are real, unequal, and negative. Output is purely exponential. These three things you should always fix in your mind. Am I clear to all of you? Okay. Now see. Let me draw this diagram. Let me draw this diagram means what? Okay. If I draw this diagram, which diagram of time is C of t. What is output? C of t. Okay. Let us say this is a desired line. So I am getting this output exponential. Okay. So this is the first phase is what? Transient phase, Ct of t. And second phase is CSS of t. What is CSS of t? Steady state phase. So you can see that output initially it is 0 and it is varying exponentially with respect to time till it reaches this point. Let us say this point is A point. So what is A point? The point where the output reaches the steady state phase. Okay. So you can see that this nature is purely exponential. Nature is pure. So why this nature is purely exponential? Because the magnitude of damping is greater than 1. Since the magnitude of damping is greater than 1, the roots are real, unequal, and negative. Which roots? S1 and S2, which we have already derived. We will just analyze it. Okay. So this is the figure. So you can see that. Now basically, guys, try to understand that very, very important point. If you see that as the value of zeta goes on increasing, zeta is equal to 2, zeta is equal to 3. Let us say zeta should be greater than 1. Imagine zeta is equal to 2, zeta is equal to 3. So I have got a two graphs. I have got a two graphs here. What is the nature? You can see the nature is purely exponential. Nature is purely exponential. Both the nature equal. Okay. So for zeta is equal to 2, you are getting settling time Ts. For zeta is equal to 3, you are getting settling time Ts. Now guys, I want to answer from your side. Can you tell me what is the difference between the two? For zeta is equal to greater than 2 and zeta is equal to 3, sorry. What is the difference do you find in this figure? Okay, you can see this is the state, let us say this is the steady state point B, this is the steady state point A. So can anybody tell me the difference? What happens exactly if I increase the value of zeta? I will explain you in the detail as I finish this particular derivation for the overtime system. But here from the figure, what do you understand? What do you understand from the figure? Anybody? You can look at the difference between the settling time. What is settling time? Settling time TS is nothing but a settling time, means what? Time taken by the system to successfully pass from the transient state and reach the steady state or reach the steady state. You can see that this settling times increases. Okay, settling time increases. How it increases? As the value of zeta goes on increasing. As the zeta increases, very very important, zeta should be greater than 1, and as the value of zeta goes on increases, this settling time will go on increases. Settling time will go on increases means what? System will take more and more time to reach the steady state. Means what? System will take more time to reach the equilibrium position. See, basically vibratory system is what? We are disturbing the system from the rest condition or the equilibrium position condition. So for a stable system, the system should reach the steady state or the system should reach the equilibrium condition. So that is why you can see that as the value of zeta goes on increasing, the settling time goes on increasing. So that is why you cannot go on increasing the value of zeta beyond a certain limit. Means what? You have to always keep some specific range for the value of zeta. Means you are saying that, sir, let us say that I am taking zeta is equal to 1000, for example. Okay, it is not the case. Depending upon the application, depending upon the condition, you have to select the value of zeta, because what happens as the value of zeta goes on increasing, as the value of zeta goes on increasing, system becomes more and more sluggish. System becomes more and more sluggish. Means what? Sluggish means what? System will resist more. Try to understand. System will resist more. Okay. Hello. Okay. Sorry. There was a mic fall down. So what I was explaining, as the value of zeta goes on increase, you can see that this graph settling time is settling time goes on increasing. Means what? As the value of zeta goes on increasing, the system becomes more and more sluggish. Means what? Your settling time increases. Your settling time increases. Means what? The system will take infinite time. System will take infinite time to reach equilibrium position. Okay, to reach equilibrium position, right? Hence that is why this overdamped system is rarely used in the practical applications. Okay, so what I mean to say is that this overdamped system is very very sluggish. Slashing time is very very high as the zeta value of the zeta goes on increasing. So that is why it is most rarely used in the most of the practical applications. Okay, but there are some applications where the you can say the old time system, this design is very very important. Okay, so we will study one by one first of all. So now let me draw this figure. Okay, there is a condition called as a H plane. Now what is H plane? Okay, what is H plane? I will draw the H plane. H plane is what? You can draw these two axes. Let us say this is a real axis denoted by sigma. This is a real axis. This is an imaginary axis. This is an imaginary axis. Okay, now this H plane means what? This is a plane, let us say. Okay, this is a H plane. So inside the H plane you can locate these roots. Now let me say, what are the location of the roots? The location of the roots are real. Let us say real, equal and negative. So let us say -2 and -4. These are the two roots. I am getting a magnitude -2, -4. Roots are real, unequal and negative. So let us say this is a 0 point. So -2, let us say this is a minus side. So I will get a two roots, -2 and -4. Okay. Now you can say that this is called as the left hand side of the H plane. Okay, I will change the color plane for you say. This is called the right hand side of the H plane. Now what I mean to say is that whenever the roots are located into the left hand side of the H plane and they are away from this imaginary axis, okay, the system is called as an absolutely stable system. System is called as an absolutely stable system. Absolutely stable system means what? The system will take a finite time to reach the steady state. Means what? Whatever may be the condition, the system will start from the zero and at some point of time it will reach the steady state. Means what? It will return to the equilibrium position. Why? This can be predicted from this H plane because the roots are lying on the left hand side of the H plane. If the location of the roots were on the right hand side, means what? Let us say roots are positive 2 and 4. If the roots were positive, then location would be on the H plane. Sorry, right hand side of the H plane. Then the system will become unstable. System will become unstable means what? I would see. I can draw the diagram like this. The diagram will become like this. Let us say this is C of t. and this is a t. Okay, so let us, this is a desired diagram. So this diagram will become like this. Okay, okay. So you can see that the output is rising exponentially. Output is rising exponentially, but it is, instead of going to the zero or instead of going to the steady state, it is going to the infinity. Means what? System will become unstable. So in such case, how will you understand after analysis? The roots are real, unequal, but they are positive. Okay, so this is what you have to understand in this case. Okay, so we will understand one by one all the cases. I hope you have understand this. Okay, so now we will solve the derivation. So I hope you have understand the theory. Zeta should be greater than 1. Roots are real, unequal, and negative. So let us say -4 and -2. So they are located to the left hand side of the S plane and right hand side. So since they are located on the left hand side of the S plane, you can say that the system is absolutely stable system. Means what? The system will successfully pass through the transient state and will reach the steady state. There is the SS of t. It will pass through the city of t and reach to the SS of t. I hope you are understanding this guy. This analysis is very, very important. Okay. So now let us solve. Now you know that mathematically zeta is greater than 1. So C upon CC should be greater than 1. So C should be greater than CC. So in this case, the first thing what I got, the damping constant C is always greater than critical damping constant in case of the overdamped system. I hope you understand this. Okay. Now C is greater than CC. Now what are the two roots? I have a two roots. S1 is equal to minus zeta plus square root of zeta square minus 1 and S2 is equal to minus zeta square root of zeta square. So now for analysis, I will consider these two roots. Now before I move on to the mathematical analysis, please message me. Have you understand this graph, both the graph and this theory behind the overdamped system? Have you understand? Please message me. Have you understand this? Anybody? Anybody can message me so can move forward. Have you understand the theory? See, as far as the oral exam is also concerned, you have to understand the theory behind the overdamped system. Okay, in the theory, they might ask you question like, for overdamped system, what is the value of zeta? What are the nature of roots? How draw a time response graph. Okay, show it on the S plane. Output is purely exponential, or whether it is purely exponential with and decreasing, or purely exponential or moving to the infinity. Okay, so all this theory you have to understand, right? So S1 is equal to this, S2 is equal to this. Okay, so now from this you can see that let us say if you put some value of zeta in this case, let us say any value, you put value of zeta in this case. Okay, you put the value of zeta. Let me see what I'm getting. So -2 zeta plus square root of 2 square 4 minus 1. Okay, and you're putting some value of omega in somewhere. Okay, so you will get some value of S1, you will get some value of S2. But important point is that value of zeta should be greater than 1. You put any value greater than 1, you will get some magnitude, and that S1 and S2 roots, whatever the value of getting, there will be always real, negative and unequal. Means what you will get, let's say -2, -4, -2 point something, whatever you are getting. Okay, doesn't matter. But it will be always real, negative and unequal. Okay, is it clear? So this is the first step. Now next step. Now what is the general solution? Now you know that general solution is equal to x is equal to e raised to minus s1 of t plus b into e raised to minus s1 of, sorry, e raised to s1 of t and e raised to s2 of t, right? This is the general solution. Am I correct? This is the general solution what I am getting, e raised to s1 of t and s2 of t. Now what is s1 of t? S1 of t is minus zeta square minus 1 into omega and t. And what is s2? Minus zeta minus square root of zeta square minus 1. So put this in equation, put this, let us say this is equation number 3. So put value of S1 and S2 in this equation number 3. You are getting this equation number 4. So what is equation number 4? X is equal to a into e raised to minus. So guys, this x is nothing but the output. This x is nothing but the output, that is equal to c of t. And on the graph, we are locating t versus c of t. So finally, whatever the graph you are getting, what I am doing, I am deriving the output equation. I am deriving the output equation c of t, or you can call it as a x also, with respect to time t. So this output equation will be will give you the characteristics of this curve or characteristics of this graph. So the characteristic of this graph and this equation will match. Accordingly, we will be deriving the equation. So finally, I am deriving the output equation. Okay. Now above constants a and b are determined by the initial conditions. So what are initial conditions? Let us say that initial condition at time t is equal to 0, because we are starting the graph from the 0. at time t. Let us say this is c of t. This is output graph what I am getting. So at t of 0, x is equal to x0. X means what? Let us say displacement. Let us say that displacement is x0. Okay. See, try to understand. I will be redrawing this graph. I will change the color plane. Okay. So let us say this is t, this is 0, and let us say this is x. Okay. So what I'm trying to say, at t is equal to 0, this x is equal to x0. Means what? Output displacement is x0. Obviously, na. And at t is equal to 0, what will be the velocity? At t is equal to 0, when time t is equal to 0, obviously velocity x dot will be 0. Okay, so these are the two initial conditions which I am doing. So put this x is equal to x0 in this equation number 4. So and put this x dot is equal to 0 and t is equal to 0 in this equation number 4. So guys, you know that this e raised to 0 and e raised to 0, because t is equal to 0, e raised to 0, a into e raised to 0 plus b into e raised to 0. Now e raised to 0 is equal to 1, so finally I am getting x0 is equal to a plus b. Is it clear? So this is a mathematics, completely a mathematical approach what I am using. So x0 is equal to a plus b I am getting. Fine. Now next step. Now I want x dot. Okay. Putting in above condition means what? This equation number 5, I have got some initial condition. T is equal to 0, x is equal to x0. Now what is the second condition? Second condition is equal to x dot is equal to 0. But first of all, to find out this is x now. So first of all, you have to take the derivation, x dot. Okay, means what? You have to derive this equation. Now how will you how will you differentiate this? Anybody? So I will directly write down the equation because I don't have much time and you have already studied differential. See how I am getting. Differentiating equation 4 with respect to time t means what? Dx by dt is equal to something I am getting, that is x dot. What is that x dot I am getting? See, a is constant, so minus zeta plus square root of zeta square into omega n into omega n. Okay, let us say this is one term, this is another term. Okay, right? So minus zeta plus square root of zeta square minus as it is into omega n into 2, derivative of t is equal to 1. So omega n plus again omega n t as it is, and derivative of e raised to minus zeta plus square root of, now you know that derivative of e raised to something is equal to e raised to x only. Okay. So you have already studied mathematics, guys. Okay. So you can open any mathematics book and you can find out the differentiation. Okay. So I am getting this x dot. So what is x dot? A into something plus b into something, and let me call this as equation number 6. So if you have any doubt in this equation, you have to look back at your differentiation logics or differentiation knowledge. Okay. So I am getting x dot. Now put this x dot is equal to 0. Put this x dot is equal to 0 and put t is equal to 0 in this equation. So after putting what I am getting, putting the initial conditions, I am getting 0 is equal to a raised to something omega n plus b into something omega n. You can see, look back here. Okay, this t is 0. Now if this t is 0 means what? This term will get 0. This term will become 0. This term will become 0. So what is the remaining term? What is the remaining term? Remaining term is this. Okay, a into minus zeta plus square root of zeta square minus 1. Because here you have e raised to something. Na? See, here you have e raised to something. Means what? E raised to 0. So this becomes e raised to 0. This becomes e raised to 0. So this term will become 1 and this term will become 1. So remaining is this term omega n and b into omega n. So only this term is remaining. I hope you are understanding this. Okay. So now I have got two equations. Equation number 5 and I have got equation number 7. Now guys, you know that you have to solve equation number 5 and you have to solve equation number 7, and you will get a and you will get b. And once you get this a and b, what you will do? This is your output equation. This is your output equation. See, why you call this x as output equation? This x is equal to c of t. This x is equal to output equation for overdamped system, which is I have to derive, which I want to derive. So output equation for overdamped system. Why? Because here you have put S1 and S2. S1 and S2 in this equation. What was the final equation, guys? Try to understand what I'm explaining you. Final equation was x is equal to a raised to s1 of t plus b into s2. But here s1 is equal to s2 is equal to, you have put the roots. Which roots you have put? You have put the roots for the overdamped system. For overdamped system, what is the nature of roots? real, unequal and negative. So you have put S1 and S2 real, unequal and negative. That is why this equation becomes the output equation for the overtime system. So once I find A and B, I will get that final equation. And from the final equation, you can calculate X easily, output. Okay, is it clear? I hope you understand. Okay, so now from equation 5 and 7. So from equation 5, what I am getting, what is equation 5? What is equation 5? X0 is equal to A plus B. Okay, so I am getting X0 minus A minus B is equal to 0 from equation 5. And from equation 7, what I am getting, see, from equation 7, I am getting A is equal to this value and B is equal to this value. Okay, right? So this is 0, na? So if I take B towards the left hand side, it will become minus B. So I am getting A. And if you take this A towards the left hand side, it will become minus A, you are getting B. So guys, these derivations are sometimes asked in an examination. So I am trying to explain it at the fullest. Okay. So is it clear? Now this is not the end basically. I have got just A and B in terms of B and A. So I have to calculate this A and B in terms of some, you can say, I have to uh, put this value of B or A in either equation. Okay. So now what we will get, what you will do, now you know that this A is value of A. So put this value of A in this equation number 5 once, and what you will get, what you will get, anybody? See what I am trying to explain. This is the value of A. It is in terms of minus B. So put this value in this equation. So here you will A will come in terms of B. So you will get the value of B. Right? This is the first step. What is the second step? Put the value of B in this equation. Here you will, this B will become A. So you will get A 2 times and you will get the value of A. So guys, what I want to explain is that once you put A in equation this, let me call this as the let me call this as equation 1. Sorry, let me call this equation 10. So put this A in equation 10 and put this B in equation 10, you will get both the values. Okay, so you can solve it at your home also. I am giving you, see. So x0 minus A minus B is equal to 0. So A is equal to what? Minus B. So minus minus plus. So XO plus B into this minus B is equal to 0. So from this solve the, make a cross multiply. So after doing a cross multiply, you are getting this value of B. So this is the final value of B. So what is B? See, now I am getting B in terms of X0. Very, very important. Okay. X0 means what? At T is equal to 0, X is equal to X0. So this is the initial condition. Okay. Okay. So B is equal to X0 minus zeta plus square root of zeta square minus 1, 2 into zeta square minus 1. Guys, is it clear? Message me, or have you understand this all? See, just solve this. Multiply this x0 by this denominator. This denominator will get again cancel here. Multiply this b with this denominator, and then then open up the brackets and solve. I have solved this properly in the notes which I have provided you in the Google Classroom. Okay, you can use it. So guys, it is clear. Message me yes or no. How I got this b? Be fast. Hello? Anybody? No any response? Anybody? Is it clear how I calculated B? No response. Okay. Thank you for no response. Okay. So x0 minus b minus a is equal to 0 now. Now put here value of b. What is the value of b? Minus minus plus. So a into this. Okay. So from this, solve this complete bracket. And what you will get? You will get the value of a. Okay. So I think you can do this as a homework solving, okay? Because we don't have so much time. It is very easy. It's a mathematical term. So finally, I am getting x is equal to x0 zeta plus square root of zeta square minus 1, 2 square root of zeta square. Okay. Now finally, guys. Now finally, what is my final equation? What is my final equation? See, I am moving here. Now I have got a value of a and b. Now this is my output equation. X is equal to. So put the value of a, put the value of e, and you are getting a final equation. Okay. What is the final equation I am getting? Yeah. So this is, so putting a and b in equation 4, and you will get this final equation x is equal to this. Okay. So put everything as it is, and this x0 upon 2, see, x0 upon 2 into square root of minus zeta square. This is in both terms because in b also and a also. So you can put this x0 upon 2 square root of zeta square. You can remove this common, and this term will remain inside the bracket. And this equation number 8. This equation number 8 is called as the output equation of overdamped system means what? Any practical system where the value of zeta is greater than 1, the nature of roots are real, equal and unequal and negative, output is always exponential, and the output equation mathematically is this: x is equal to, this x is nothing but c of t. What is c of t? Output equation, because this is a time response analysis, and that is why we are always taking in terms of t. So guys, as an you can say a derivation, your final output equation will be x is equal to this. Now message me. Now I will explain the characteristic curve. Now I will explain the characteristic curve. Now characteristic curve means what? This characteristic curve represents the output equation. Okay, output equation means what? Let us say, let me draw this time response graph. Okay, let me make it simple. So let us, this is time. What is this? This is C of t. C of t means what? This is x. Okay. So how is the output there? Okay, means what? This is x. C of t is x. Let us say this is 0. Okay. So output curve is like this. Okay. Output curve will be like this, for example. Okay. This. Okay. Now you can see what you can understand from this. What you can understand from this, if I draw, this is the CT of t, transient phase. Now you can see that here at a transient phase, output is varying exponentially. It is a exponentially. Output is varying exponentially. Why output is varying exponentially? Because here zeta is greater than 1, roots are equal, unequal, negative, positive. And here this is nothing but a CSS of S. Means what? The output is steady state. Now you can see that in the graph I have shown you, that is in the S plane, xi to omega, the roots are located here, -4 and -2, let us say, left hand side of the H plane. Now roots are located on the left hand side of the H plane means what? Your system is absolutely stable. Absolutely stable means what? It will reach the steady state. If the location of the roots was like this graph would have become like this. Maybe it would have decreased and it would have gone to the infinity. It would, without reaching the steady state, it would have gone to the infinity. I hope you have understand this. So this is the interconnection between the nature of the roots, value of the damping factor zeta, location of the roots. Okay. So this is all, guys, you have to understand. Okay. So now I will draw this diagram again. So this is the actual characteristic curve. So you can see that this, if I draw this like, okay, if I draw like this, if I take, this is actual characteristic curve, na? It is reaching steady state. Okay. So if I draw this line like this, you can see that it is exponential. So that is why, now guys, one more point you have to understand, that in this output term, you can see that the value of, there is a E. Okay, so in equation, there is a E means what? The output will be exponential. The output will be exponential. And there is a E raised to negative, E raised to minus zeta. Negative means what? Negative means what? You can see here. Negative means what? If there is a negative sign, E raised to negative sign means what? This curve will reach to the steady state. Okay, I will draw the another curve. T. If I draw like this, if I represent like this, let us say this is C of t and it is x. So this will reach to the steady state. Why this is reaching to the steady state? Because first of all, it is exponential. So there is E over here and there is a negative sign. So if it was E raised to positive, can anybody tell me if in the equation, if there was E raised to plus sign, what would have happened? Anybody? If there was a plus sign, how would you represent this graph? Very simple. This graph would have gone like this, infinity. Right? Means what? Means what? If I draw the location here, the roots were present into the roots. The location of the root will be the right hand side. Okay. So now message me. Have you understand this or not? Yes. Hello. Okay, so this is all about. And one more point, very, very important, that here e raised to minus sign means what? This transient phase will vanish. Transient phase will vanish means what? Let us say this is a transient phase. So output will vary with respect to time, and then this will become 0 and it will reach the steady state. Okay. Okay. So basically, finally I can say that this displacement x, you can see it is a sum of, this displacement x is a sum of two vanishing, is a sum of two vanishing exponential is a sum of two vanishing exponentials with initial values. This is a final story. Okay, moral of the story. Okay, x is equal, let us say this is common, so sum of two vanishing exponential means what? One is a, this, and second one is b, right? So this is one, let us say a, and this is b. So we have two exponential, this is one exponential and this is two exponential, and these two exponential have e raised to negative power, means what? They will vanish. They will vanish means what? The system will not remain in the transient state, it will reach to the steady state, and it is having two initial values a and b, which defines the initial condition. Okay, so this is what the moral of the story. And one more point, I have told you that as the value of zeta goes on increasing, I will just repeat once again for your better understanding. As the value of zeta goes increases, okay, as the value of zeta increases 2, 3, the system becomes more and more sluggish. Since system becomes more and more sluggish, this settling time increases. Now, since settling time increases means what? What will happen? Okay, the system will take infinite time to reach steady state, infinite time to reach the steady state, or you can also call it equilibrium position. That is why this particular overdamped application is rarely used, not commonly, sorry, most rarely used in most of the practical application. Why? Because settling time goes on increasing, system becomes more and more sluggish. Means what? The system will resist more and more. Sluggish means what? The resistance goes on increasing. I hope it is clear to all of you. Okay, so that is why instead of using a overdamped system, most of the practical cases we are using a critical damped system. Now let us understand what is critical damped system. Now critically damped system. Okay. Now critically damped system is the second type of system which you will find in most number of applications. I will also give you the application also. The first is zeta is equal to 1. Now try to understand that zeta should not be equal to 0.99. Zeta should not be equal to 10.1. If it is 10.1, it is overdamped. It is 0.99, it is underdamped. When the value of zeta is equal to 1, it is called as a critically damped system. So exactly the value of zeta should be equal to 1. Now guys, try to understand that when the value of zeta is equal to 1, what exactly happens? The roots are real, equal and negative. In that case, what was the nature of root? Now guys, I hope you have understand. Uh, the behavior of the system, whether it is oscillatory or whether it is exponential, depends upon the nature of roots, and again the location of the roots also depends upon the nature of the roots. Okay, so basically I can write like this. Okay, so there are parameters, let us say mck, parameters of a. So on these parameters, mck means what? Parameters of a physical system. Let us say physical system. This is a physical system. You have converted this physical system by using a steps involved in the vibration analysis. That is a mathematical modeling. By doing a mathematical modeling, you have converted this physical system into MCK. Depending upon this MCK, depends upon this MCK will be the nature of roots. Nature of roots वरती काय डिपेंड असेल? Location. And on location, behavior. Behavior or nature of the system. Okay, is it okay? So this is the graph what we are following, right? Okay, so now here again roots are real, equal and negative. In last case it was unequal. You can see this is a change, it was unequal in over time. Output is again purely exponential, but very important, the settling time is less as compared to the overtime system. Means what? The settling time is very less, means what? There is less resistance for a system to reach to the steady state. There is a less time for a system takes less time to reach the steady state or to return to the equilibrium position. Okay, and one more important point, this zeta is equal to 1 is called the critical value of zeta, because if the value of zeta is less than 1, means what? Let us say it is zeta is equal to 0.99. Okay, the further roots will become complex conjugate. Further roots will become complex conjugate. Means what I want to explain is that zeta is equal to 1 is a least value, or you can say a minimum value of zeta where the roots are real. If you decrease the value of, see, if you go on increasing the value of zeta, let us say zeta is equal to 1, 2, 3. If you go on increasing, the roots are real. The roots are real, but they will become unequal. But the system becomes more and more sluggish, and the settling time goes on increasing, and it will take very large time to reach the steady state or return to the equilibrium position. But zeta is equal to 1 is the only value where if you decrease the value of 1 zeta be less than 1, if you make the value of zeta less than 1, the roots become complex conjugate. And the exactly what happens, the behavior of the system will change. The behavior of the system will change means what? For zeta is equal to 1, the graph is like this, exponential. For zeta is equal to 2, again the graph is like this, but the settling time is less. Let us say this is a settling time. Let us say this is a settling time. So this is zeta is equal to 2, this is zeta is equal to 1. But if you decrease the value of zeta, you can see the nature of the system will change and the nature will become oscillatory. And this is where the zeta is less than 1 but zeta is greater than 0. So this is called as a underdamped system. This is called as a underdamped system, and this is called as a critically damped system, and this is called as a overdamped system. So these are the three types of systems. So for underdamped system, for the underdamped system, what is the nature of roots? Nature of roots is complex conjugate. Complex conjugate. What do you mean by the complex conjugate? Minus 1 plus I. So minus 1 is the real part, I is the complex part. This is a real part, this is a complex part. You know, na, mathematics. So for underdamped system, the value of as the value of zeta becomes 1, greater less than 1 but greater than 0, the nature of the system become, because the location will also change. Na? What is the location? This is a location. So here you have a I. So some roots will go on to this imaginary axis or it will locate like this in the space. Okay, because that I will explain you later on. Okay, don't worry in the detail. So nature of the roots are complex conjugate, and here the nature of roots are real, negative, but equal. But as you increase the value of zeta from the 1, it becomes again real but unequal. Okay, so this is the difference between the analysis. So depending upon the type of the application, you have to design zeta. Please message me, have you understand this comparison? That is why zeta is equal to 1 is called the critical value of the zeta, and this system is called the critical damped system. Okay, I hope you have understood this. Okay, so now you can see this graph. Okay, you can see this graph. Zeta is equal to 1. You can see that settling time is decreased. If I say zeta is, if you want to look at zeta is equal to, what would have happened? It would have happened like this. Okay, so this would be the settling time. You can see that settling time is increasing. If I take zeta is equal to 3, again settling time would have increased. So settling time goes on increasing, guys. Settling time is what? Time taken by the system to reach the steady state or to reach the equilibrium position. Okay. Now, location of the roots, very important. See, roots are equal and negative. Means what? Let us say roots are minus 2, minus 2. Means let us say roots are minus omega n and minus omega n. These are the two roots, minus 2, minus 2. So their location will be where? At the same point. So such a system is called as absolutely stable. Overdamped system is also called as absolutely stable, but here very important point, settling time is less. So let us take an example. So this critically damped system is used in lot of applications, like you can say, you can take as an example of a gun, firing gun. You know a gun. So the gun, a huge heavy guns which are used for a firing. So there you have a trigger. Okay, so inside that trigger you have a spring mechanism, right? You have a spring mechanism. So what exactly we do? Once you press the trigger, what will happen? The bullet will get fire, and automatically that trigger, which is moved from its original position, it will again return to its equilibrium position, right? It has to reach to its equilibrium position at an earliest. Otherwise, what will happen? If you fire a one bullet and let us say the trigger is not moving to its original position, you have to wait some time to fire the bullet, and then the opposite army, the opposition army would have fired you, right? Would have fired a bullet on you because you were waiting for a trigger to come back to its original position because you have used the overdamped system. Or if you have used the underdamped system, there will be a large oscillations inside the trigger. I hope you understand this. Okay. So that is why there you have to use this critical damped system. So once you fire the bullet by using the trigger, okay, what would have happened? It would have reached fast to its original position, so you can fire the another bullet. So that is why this critical damping system is very important. Next, you can take an example of a automatic. You can take an example of a automatic closing and opening, automatic door closing and opening. You know, have you seen automatic door opening and closing system? So there also, if you use a overdamped system, and if you open the door, it would have taken long time to close it again or long time to open it again. So that door should open automatically fast and close automatically fast within a mean time. So these are some basic examples where you will use this critical damp system. Okay, you will design this damping because you have to design your damper, design your damping in most of the application. So how will you design? So for that you have to do this mathematical analysis. So is it clear, everybody? Okay. So now basically try to understand that within a 5 minutes we'll finish off this. Now you know that you know the theory. So now you know that zeta is equal to 1. So C upon Cc is equal to 1. So C is equal to Cc. Now guys, very important for critical dam system, for overdam system, your C was greater than Cc, right? But for critical dam system, your C is equal to Cc. So when C is equal to Cc, right? So such a system is called as a critical dam system. Okay. So now what is the roots? First of all, how will you find out the roots? The roots will change, na? The roots will change. First of all, let me write down the roots. Then you will understand properly. Let us say what is S1? What is S1? Minus zeta plus square root of zeta square minus 1 into omega. Okay. And what is S2? Minus zeta minus square root of zeta square minus 1 into omega. Okay. Is it clear? Now, if zeta is equal to 1, if zeta is equal to 1, put zeta is equal to 1 here. So what you will get? S1 is equal to minus 1 plus 1 plus 1 into omega n, right? Sorry, minus 1 plus 0, minus 1 plus 0 into omega n, right? So what you're getting, S1 is equal to minus omega n. Similarly, you put here minus 1 minus square root of, again here it is 0 only. So you are getting minus 1 into omega n, right? So you are getting S1 is equal to minus omega n, S1 is equal to minus omega n. So what I was telling you, you are getting the roots are real. Let us say value of omega n is 2 radian per second. So roots are real, equal and negative. Okay. So if roots are real, equal and negative, what will be the location? Location is sigma I omega. So these are the locations of roots minus omega n. Whatever will be the value, minus 2 or minus 4 radian per second, zeta value or something. Okay. Is it clear? So roots are real, equal and negative. So general equation for repeated roots. Now, guys, what was the general equation for unequal roots? The roots which are not repeated, the general equation is x is equal to a raised to s1 of t plus b into e raised to s2 of t. But now here the roots are repeated, na? So you cannot use this general equation. So you have to use this general solution equation. X is equal to e raised to s1 of t plus b into t s2 of t, right? So here extra addition is b into t, e raised to s2 of t. So t is nothing but extra addition. So t into e raised to s to t. Why? Because the roots are repeated. I hope you have understand why I have changed the general solution. Is it clear, all of you? Okay. Otherwise, if you use the general solution, what you are using for the overlap system, it is wrong because here the roots are repeated. Very important. Okay. Now, so x is equal to a into what is h1 minus omega n t plus b into t raised to e raised to minus omega n t. Now this equation is very easy. So equation number 8. So now let t is equal to 0, initial condition, x is equal to x0, t is equal to 0, x dot is equal to 0. So anybody tell me what will happen? So you'll get x is equal to what? What is x? X is equal to x0. Now here t is equal to 0. Those t term will become 0 and this term will become 1. So x0 is equal to a. So x0 is equal to a. So this is the first. So what is a? A is x0. See, this equation becomes, see, for critical dam system, the derivation is also very easy, as the system is very easy. Okay. So now I have got one first. Putting t is equal to 0 and x is equal to 0, I have got x is equal to a. Now next x dot. Now anybody can tell me how you derivate this x dot is equal to a into e raised to minus omega n t plus. Now here you have to apply the UV rule. UV rule because you have two terms of t. You are differentiating with respect to t, na? So you have to apply the UV rule, that is a product rule. T into derivative of e raised to minus omega n t plus e raised to minus omega into derivative of t. So by taking the derivative, I am getting this. So differentiating equation 8 with respect to time, I am getting minus a into omega n e raised to omega t plus b into Apply the UV rule, you are getting this. Okay, so after derivating you are getting x is equal to minus my b e raised to minus omega t minus a plus bt. So this is equation 9. Now apply the initial conditions. What are the initial conditions? Putting initial conditions, x dot is equal to 0 and t is equal to 0, you are getting this only, because see, this will become 0, this term will become 0, and this term will become 1. So we are 1. So we are getting a into, sorry, this term will become b 1, and here you are getting what? Minus a into omega n into omega n, right? So you are getting what again? B is equal to a into omega n. So b is equal to what is a now? What is a? A is equal to x0. So what is b? X0 to omega n. So I have got two initial conditions. See, I have got both arbitrary constants. A is equal to x0 and b is equal to x0 into omega n. Is it clear, guys? Is it clear or not? Please message me. Okay. So final general solution. What is equation for general solution? X is equal to a into e raised to h1 of t plus b into t e raised to h2 of t. So what is h1? Minus omega n. Sorry, what is h2? Minus omega n. And what is a x0? And what is b? X0 into omega n. So finally you are getting equation, output equation, x is equal to this. So this is called as the output equation for PTO system. Now you can compare the output equation x is equal to CD. You can compare the output equation x is equal to CD for the overdamped system and output equation for this equation. In both the equations are different. Both equations are different, but what is the common thing? Both is having an e term and e raised to negative term. Means what? Means what? This system will, this exponential term will vanish. This exponential term will mean, the exponential term means what? It is a transient term. That transient phase will vanish and the system will reach the steady state. Means what? System will reach to the equilibrium, but within a less time as compared to the overdamped system. So that this is the biggest advantage of this equation. Now let me draw the characteristic curve. So this is the characteristic curve. You can see this is a CT of t transient phase. This is CS of t steady state phase. You can see that, and this is a settling time TS, and this curve depicts this equation E plus B into D e raised to minus omega t. Okay. So guys, so now last case number 3 is underdamped system. So this I will explain you in the next lecture. So now if you have any doubt, you can message me. So this is from my side for this particular lecture. Okay. I hope you have understood.